Welcome to HEC Physics. This is our second video on translational motion. In our previous video, I have explained the concept of momentum and impulse. So if you haven't watched that video, then I would recommend you do that first because we will use some of the concepts I have explained over there in this video. In this video, my plan is to go over conservation of momentum, which is another extremely important concept we have to use in analyzing translational motion. And then depending on time, I'll see how it goes. We might cover center of mass as well, or make a separate video about center of mass. In translational motion, we often have to analyze situations where there are multiple objects that are moving in straight lines and then they collide with each other. So basically, we have to look at collision problems or the opposite, where you start with one object and then it explodes into multiple pieces. So we are looking at explosion problems. In analyzing these problems, the physics principle of conservation of momentum is extremely useful, and we often have to apply that for the analysis and calculating different quantities in collision and explosion problem. You might be familiar with this physics principle from year 12. What this principle tells us is that if you have objects colliding or exploding, then the total momentum of the system, and we are not talking about individual momentum, but the total momentum of the system of all the objects is conserved. And conserved means it's the same. So it stays the same before and after collision, if it's a collision problem, or explosion. And this happens only when there is no net external force. This is very important, that is acting on the system. If there is external force, then definitely the total momentum will change. Now, what are the common external forces that we often have to consider? The common external forces are friction. So if we are looking at a collision problem on a frictionless surface, then we can apply conservation of momentum. Or it could be gravity. So if we are looking at a problem in outer space where gravity is negligible, then we can apply conservation of momentum as well. But for situations where these are not true, the total momentum of the system can change. Now let's look at an example problem where we have to apply this principle of conservation of momentum to analyze collisions in level 3 physics. Now all the problems that you are going to analyze using this principle here in level 3 physics will be two-dimensional collisions. So it will be problems where objects are colliding in 2 dimension, or it could be explosion problem, but it will be in 2 dimension. So what we have is an object moving in this direction. Its mass is 0.6 kg and it's moving at 1.80 meters per second on a frictionless surface, and then it collides with another object which has a slightly smaller mass, 0.5 kg, and it's stationary, so it's not moving. So this is the situation before collision. And then they collide with each other, and then after the collision, 0.6 kg object moves in this direction over here, and we know that it's moving at 1.10 meters per second. And the other object, the smaller mass, 0.5 kg, moves at an angle 90 degree to this. So over here, it's making an angle of 90 degree over here with the 0.6 kg mass, and it's moving in this direction, but we don't know the speed. We don't know the speed after the collision for this 0.5 kg object. So this is the situation before collision, and this is the situation here after collision. Okay. So in this kind of collision problem, we will apply conservation of momentum. So first, we are either given that it's moving on a frictionless surface, or sometimes they ask you state any assumption that you have made. So over here, we are going to assume that the objects are moving on a frictionless surface. So therefore, we can apply conservation of momentum, the principle of conservation of momentum. So applying conservation of momentum, we can say that the total P momentum before the collision has to be equal to the total momentum after the collision. So whatever is the speed or the velocity of this object here, it will be such that if I add the momentum of the 0.5 kg and 0.6 kg mass after the collision, it should be equal to the total momentum of these two before the collision. Now, looking at the question, we know that we have the mass and the speed given to us for both objects before the collision. So we can work out what is the total P before the collision. It should be the momentum of the 0.6 kg mass plus the momentum of the 0.5 kg mass. And we know we can use the P equals to mv formula. So mass is 0.6 for the first object and its velocity is 1.80, and it was moving in this direction, so the momentum should be in that direction as well. And then for the second one, the mass is 0.5 kg, but it was stationary, so its velocity is 0. So if you do this calculation, then you get a total momentum of 1.08 kg meters per second to the right. The second term will be 0 because anyway, multiplying anything with 0 gives you 0. So this is the total momentum before the collision. And based on the principle of conservation of momentum, this should also be the total momentum after the collision. Okay. Now we know that the total momentum after the collision, so this total P after the collision is equal to the momentum of the 0.6 kg mass, which is going up at an angle, plus the momentum of the 0.5 kg mass, which is going down at an angle. Now we can work out how much this is because we know the mass and the speed after the collision. So we can use 0.6, which is the mass of the object, times the speed, which is given to us in the diagram. So if we go back to the diagram, it's 1.10. So we can put 1.10 meters per second over here. And then that will be going up at an angle like that, plus the momentum of the other object, which we don't know, we have to work it out. So this becomes 0.66 kg meters per second, and this is our unknown momentum. And we know what is the total momentum. We know it's 1.08 kg meter per second, and it has to be to the right because it should be same as before the collision. So what we can do now, we can draw a vector diagram where we add these two momentums in the vector diagram, and what we should get is this momentum over here. So we'll start with drawing the first 0.66 momentum, which is going up at an angle. So this is our 0.66 kg meter per second momentum. And then from the head of this momentum, we are going to draw the momentum of the 0.5 kg mass, which is at 90-degree angle to this first one. So it will be kind of going down like this. And this is the momentum of the 0.5 kg mass, which is unknown. And these two added together from start to finish should give me a total momentum, which is going to the right, because this over here is the total momentum. It's 1.08 and it has to be to the right. So that's how we drew the vector diagram, adding the two momentum of the objects after the collision should give me this 1.08 to the right momentum back. So this is a right angled triangle over here, and this angle, the angle between the two momentum, is 90 degrees. So using Pythagoras, we can work out this unknown momentum over here. So this should be the longest side square, 1.08 square, which is opposite to the 90-degree angle, minus the shorter side square, which is 0.66. So if you do this calculation, then you will get the momentum of this object over here, the 0.5 kg mass, which turns out to be 0.8548. So because all my numbers are given to two significant figure, I'm going to round this to two significant figures. So 0.85 kg meters per second is the momentum of this 0.5 kg mass. Now we are not done yet. We have one last part to do because the question asks us to work out the speed, not the momentum. We have to apply the principle of conservation of momentum to work out the momentum first. And now that we know the momentum, we will use the relationship P is equals to mv to work out the velocity, which is momentum over mass. We know the momentum of the 0.5 kg mass, it's 0.85, and we know its mass is 0.5 kg. So if we do these two, then we will get the momentum, which is 1.7 meters per second. Okay, so that's our final answer. We have worked out the speed of the 0.5 kg mass over here. This was one way of working out the momentum of the 0.5 kg mass. There's an alternative way of using vector diagram to work out the same momentum after the collision, which is where we start with this fact that the total momentum after the collision, which we already know, it's 1.08 kg meters per second. And we also know that should be equal to the total the momentum of 0.5 kg mass and 0.6 kg mass added together. And we know the momentum of 0.6 kg mass because we know its mass and velocity. So then to work out the momentum of 0.5 kg mass, what we can do is we can subtract this momentum of 0.6 kg mass from the total momentum that we already know. So what we can do alternatively is to work out the momentum of the 0.5 kg mass, the unknown. We can use the total P after the collision, which is same as total P before the collision, minus the momentum of 0.6 kg mass. So we can use 1.08 kg meter per second, which is the total P, and it's to the right, minus we have worked out the momentum of the 0.6 kg mass after the collision is 0.66, and it's up at an angle. So if we subtract these two vectors, we will get the momentum vector of the 0.5 kg mass. And I have explained in the impulse part in the previous video that if you have to subtract two vectors, you keep the first vector as it is and you change the subtraction into addition, and then you have to flip the direction of the second vector. So now we can draw our new vector diagram where we want to add these two vectors. So I'll draw the first vector, which is 1.08 to the right. So this is our total momentum. And then we draw the second vector, which is the 0.66 kg meters per second, and the momentum of the 0.5 kg mass will be at 90 degree to this momentum over here. So this is the momentum of the 0.5 kg mass, and it's making an angle of 90 degree because from the diagram we know the two momentum after collision are at 90 degree to each other. So same process, we can work out what is the momentum of this. It will give you the exact same answer. We take the hypotenuse, square it, longest side square opposite to the 90 degree angle, and then subtract 0.66 square from it. And if you do that, you will get the exact same answer as before, which is 0.85 kg meter per second. And then you can use that to work out the speed, the same process which I have shown you earlier. So this is just to show you that instead of vector addition, you can also do vector subtraction to work out the unknown momentum. Now there's one more thing that I want to specify over here. Even though the total momentum of the system is not changing before and after the collision, the momentum of individual objects can change during collision because there is no net external force acting on the system to change its total momentum. But as the objects are colliding with each other, they are applying forces on each other. So if you focus on just the 0.6 kg mass over here, then as it collides with the 0.5 kg mass, the 0.5 kg mass will be applying a force on it. And similarly, there will be an equal and opposite force acting on the 0.5 kg mass because of the 0.6 kg mass. So the two masses are applying equal and opposite forces on each other. This is Newton's third law of motion. Every action has equal and opposite reaction. So there are internal forces, and these internal forces are always equal and opposite. And because of that reason, the momentum of individual objects in the collision can change. So you can see initially the 0.6 kg mass was moving to the right, and then after the collision at 1.80 meters per second, and then after the collision it's moving up at an angle at 1.10 meters per second. So definitely the momentum of this mass itself has changed, and you can work out the change in momentum or the impulse of this mass by considering this as the initial momentum, and then you can work out what's the final momentum and then subtract the two to find out what is the change in momentum. And once you work out what is the change in momentum delta P of the 0.6 kg mass, you will see the change in momentum of the 0.5 kg mass should be exactly equal but in the opposite direction. So that these two change in momentum, they cancel each other out, and overall there is no net change in momentum, and that's why the total momentum of the system remains constant. So that is something that you need to keep in mind. Now, in all collision or explosion problem, we know that the total momentum of the system is always conserved if there is no net external force. But based on the total kinetic energy of the system, we can have two types of collision, and these are known as elastic collision or inelastic collision. And the difference between these two is that in elastic collision, the total momentum is conserved, but then on top of that, the total kinetic energy of all the objects in the system is conserved as well. Now, when you're adding the kinetic energy, remember energy is a scalar quantity. So you simply work out the kinetic energy using the half mv square formula. And if you do that for all individual objects in the system and then add them up, you get the total kinetic energy, and you will see that it is same before and after the collision in elastic collision. On the other hand, for the inelastic collision, this is not conserved. So the total kinetic energy is not conserved. That means there might be some of the kinetic energy that is lost and it transformed into other forms of energy. A good example is explosion, where you start with a single stationary object, and because it's stationary, its kinetic energy is definitely zero before the explosion. And then if it explodes into multiple parts and then these different parts fly off in different direction, then you know that they definitely have kinetic energy because they're moving. So the total kinetic energy after the collision is definitely not zero. So over here, some of the potential energy stored in the object has now converted into kinetic energy, and that's why the total kinetic energy after the explosion is greater than zero. So based on the kinetic energy, we can have two different types of collision: elastic or inelastic collision. So this was everything from conservation of momentum. And because this video has already become quite long, I'm not going to cover center of mass in this video, and I'm going to make a separate video about center of mass. So this is where we finish today, and keep an eye on the channel. I will post the center of mass video pretty soon.